Hi everyone, thank you so much for coming and thank you for the introduction. If you're worried about missing Dragon's Den, I'm very happy to take some of your money, don't worry. I can pitch it for you now. So yes, my name is Veerle, I'm a biomedical engineer and I focus on leveraging the power of sound waves to tackle healthcare challenges. And today I specifically want to tell you a story about back pain. So I'm sure either you or someone you know has experienced back pain before. If you haven't, lucky you, and also just you wait. As back pain, other than the common cold, is the most common reason for people to visit the doctors worldwide. Over 600 million people worldwide experience chronic back pain, one of whom is actually my mother. I remember being as young as 8 years old when I visited her in the hospital after her surgery. I only went once because I found it really difficult to see her like that. It's hugely debilitating for her and it prevents her from partaking in activities that I take for granted, like exercising, having a job, and seeing her daughters graduate without pain. Now, back pain is predominantly caused by degeneration of the spinal disc. The spinal disc is the shock-absorbing cushion that sits in between the bones in your spine and allows you to walk and jump up and down without any problem. So that didn't cause me any pain. Now, this spinal disc is also the cushion that gets compressed during the day. So it's the reason that you're a little bit less tall at the end of the day than when you first wake up. Or for astronauts, for example, to be taller as they return from space due to the lack of gravity. Now, due to environmental factors like obesity as well as aging, this elastic cushion that absorbs the shocks in your spine decreases in height. It's something called degeneration. And I can illustrate that. We'll see if this works perfect. This is my mother's scan, and this is her spine. And these black bits are the spinal disc, so the cushion in between the bigger bones. And as you can see, as we move down the spine, some of them are a lot less thick. And as we go down very far, she actually almost misses her entire spinal disc, which means that every time she moves, her bones bash together, causing a lot of pain. Now, conventional treatment options at the moment are conservative physiotherapy, which is just symptom management really, or costly and highly invasive surgery, which often shows pretty poor outcomes. For example, for my mum, as she is still suffering daily. Now, a lot of scientists have come up with alternative ways of treating. So, for example, by injecting a liquid to pump up that spinal disc, which then hardens over time, either through chemical reactions or through the addition of light. Now, that sounds really good, but the problem with those techniques is that it's really difficult to control the precise location as well as the timing of that hardening process, especially deep inside the body. Now, that's where my work comes in. So I work on ultrasound. Kester already mentioned that briefly just before the break. I'm sure you're familiar with ultrasound from scans of pregnant women where they visualize the baby inside the mom's tummy. Now, if you change the parameters a little bit, you can actually use ultrasound therapeutically as well. So ultrasound is ultimately just sounds like what you're hearing right now, but at such a high frequency, or in other words, pitch, that you and I can't hear that anymore. But it's actually really interesting, just above what we can hear, your pets, like your dogs and cats at home, can, for example, still hear those frequencies. Now, a property of ultrasound is that it can penetrate much further into the body than light can, and it has the ability to be focused in a very narrow spot. And that is very similar to what we do with light. Now, I did this in school, but I've learned as I've been practicing this talk that this might just be part of the Dutch curriculum. So if you want to give this a go at home, the disclaimer is that be careful. But this is a magnifying glass, and I learned in school how to use that to focus light. So I'm going to try and do it with the stage light, and we can see there's loads of spots here, so I'm going to get loads of spots here. But I'm able to focus that very broad, diffuse light into a very narrow spot. And if I leave it long enough, it will actually start a fire. Don't worry, not going to happen, even though you know where the exits are. So the same thing we can do with ultrasound. And what that means is that in this very localized spot, in depth inside the body, we can cause the temperature to rise. Don't worry, we're not burning anything. We're just slightly elevating that temperature without causing any problems to any of the tissues in between that path. And it's precisely this property of ultrasound that I'm using in combination with materials that respond to changes in temperature to craft tunable gel spinal disc implants. Now, let's take a step back. So the material that I'm using is a liquid, which means it's injectable. And you can see me mixing that here. It consists of 2 components. The first one is a sugar solution. And the second one is lipid vesicles, so very small lipid vesicles that are filled with calcium. Now, these lipids have as a property that if they are heated to 41 degrees, so just slightly over body temperature, they change shape, causing them to become leaky. That sounds like a bad thing, right? No one wants leaky pipes. But actually, the calcium that leaks out is able to cause our sugars in our first component to kind of link up together and form a big network. And what that means is that using ultrasound, we can gently heat to 41 degrees, calcium is released, a network is formed, and what was a liquid upon injection, so only needed a needle injection, is now a gel inside the spinal disc. Now, in order for me to test that, I had to come up with a test chamber that was able to simultaneously expose my sample to ultrasound to heat, measure the temperature inside my sample holder, and then lastly, record cavitation emissions. Now, what is cavitation? So ultrasound is just a wave, like Kester said as well. So it's got high pressure and low pressure, and it changes like that. If that wave is of sufficient amplitude, so big enough, it's actually capable of forming bubbles. And the way that I can explain that best to you is I've brought this sparkling water bottle, and it's filled under pressure. So there's a high pressure at the moment inside this bottle. The moment I open it, the pressure will drop, and I'm actually going to see some bubbles form. Effectively, that is similar to what we do with sound. So it's these negative or like low pressure drops that are causing these bubbles to form in our material when we expose it to sound. Now, once these bubbles are formed, they will actually move to the sound wave. So as the wave changes, these bubbles will move and almost dance in the field. But at some point, they can't keep up because the wave is changing so fast. So what happens then is they collapse. And just like you could hear me clap right now, that produces a sound. You can think of it like dropping a pebble in a pond and it causing all the ripples. Now, this sound is way too high pitched, again, similar to the sound I'm sending in, for us to hear. So luckily, we have devices in the lab that are able to hear this sound by picking up these ripples in the water. Now, I'm controlling the ultrasound treatment that I'm giving my material such that the temperature always remains between 41.5 and 42.5 degrees Celsius. So this, if you remember, is high enough to cause my calcium vesicles to start leaking the calcium, and therefore for my lipids to link up and form a network and thus a gel, but it's very safe and very controlled. And the result is these white jellies. They look a little bit like gummies. So this is my first spinal disc implant material. Now, these are mechanically tested because obviously we want to see if they perform similar to the native human spinal disc material. And I'm very happy to say that upon these first tests, at least we're in the right order of magnitude in terms of the mechanical properties and in terms of how they're performing under compression as well as like shear stresses. So basically the twisting motion of your body. Now, I told you something about the formation of these bubbles that are appearing in my material. And interestingly, we have found out that they actually are an indication of how well my treatment is going. And I will tell you why. So these bubbles are formed once I hit them with ultrasound. And as long as it's a liquid, they can move. They're doing a great job moving and therefore producing sound. Now, as my material gels, so as my treatment is more successful, these bubbles can't move as much anymore because they're pushing against the gel. So actually, they can't move as much and therefore can't produce as much sound. You can think of that like swimming in a swimming pool of water versus trying to swim in a swimming pool filled with, I don't know, honey or glue. Obviously, that's a lot more complicated. So I told you initially that the bubbles produce a sound that is so high-pitched that you and I can't hear that. But for the purpose of this talk, I've transformed my data so that we can. So just a little disclaimer, it's going to make some noise. It's as if you're hitting all of the keys on the piano at the same time. And the first sound I'm going to play is a sample that contains my sugar solution, but it doesn't contain the vesicles with the calcium. So what that means is there's no calcium, so my sugars can never link up, never form a network, so it will always remain a liquid. Now this is what it sounds like. So as the recording progressed and as my treatment progressed, at least, maybe you guys have way better hearing than I do, but I can't hear a difference. It sounds exactly the same at the start as it does at the end. So I'm going to play that for you one more time, just so you have a good reference of it. Now in comparison, I'm going to play you one that is actually a material that contained these calcium vesicles, and therefore as my treatment progresses it will start to leak and it will start to become a gel. Now I want to hear from you guys if you can hear the difference. So what are you guys hearing? What is the difference? More stable at the end, yeah? Anything else? It's quieter, exactly, yeah. The sound goes down as my treatment progresses. I will play it one more time, you can listen out for it. So I'm currently very much in the process of trying to see if I can utilize that change in sound as a metric for whether I'm successfully causing this gel. And I'm also, because this work started, like many experimental techniques that you've seen tonight start in plastic dishes or test tubes or whatever, I'm trying to move into a slightly more realistic model, and we do that in cow spines that we get from the butcher. So you can see me preparing that here. As a vegetarian, that's not the favorite part of my job, I can assure you that. So we're very much in that stage right now of this work, and if you would like to learn a bit more about this work, see where it's going, or just support women in STEM, you can scan this QR code, which will bring you to Instagram to follow me and my colleague Sarah on Instagram to basically get a little bit of a look behind the scenes. So I want to finish with saying that I started this project about a year ago, and we've taken it from conceptualization to proof of concept. And we've been able to generate these spinal disc implant mimic materials of same order of magnitude mechanical properties as the normal spine. Now, of course, like any experimental product, it's going to take a lot of testing and some optimization over the years, but this is a very promising first step in developing a treatment approach that is non-invasive, not costly, and will give people like my mother agency over their life back. Thank you.